Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on carbonyl compounds. So this is topic 17 of the CIE specification, so that's the Cambridge Internationals. So in this video, as it suggests, we're going to look at compounds containing the carbonyl group, which will include obviously aldehydes and ketones and carboxylic acids and all of them different types of molecules, and look at the reactions of them. Obviously this is one of the topics. There are loads of topics to do with the CIE syllabus for year 1 and year 2, and all the full range of the A-level videos are on my channel, which is Allery Chemistry. I would much appreciate it if you could subscribe to the channel just to show your support. That would be really good. The videos that you see here, the actual slides, PowerPoint slides that you're available to purchase, and you can purchase them as a bundle, i.e. organic chemistry if you wish, or the full A-level if you wanted to. They're great value for money. The link is in the description box below. Click on that and go and have a look at them. But they're great for revision. You can have them electronically, obviously on your phone or your tablet or anything like that. So they're really good. So go and have a look at them on there as well. Right, so let's have a look and see what we've got here. So this is obviously looking at, I should probably say this, I say this nearly every video to do the CIE. The topics do merge together quite a lot. There's a lot of overlap, so there's a lot of bridging. So typically what I would probably say is make sure you understand all of the previous topics, so have a reasonable understanding. I'm not saying you're going to be an expert at it, but have a reasonable understanding of what's gone before this topic here. I'll try and bridge as much as I can between the different topics and kind of refer to them, but it'd be a good idea if you can just check them through first. Some of the things I'm going to assume that you know them basically or bits and pieces from previous topics, so that's why I'm saying that. Right, okay, so let's start with obviously an introduction first to the oxidation of alcohols first. Obviously carbonyl groups are made or can be derived from alcohols, and it kind of fits quite nicely with the previous topic, which is obviously hydroxy compounds, which is topic 16. So this one's going to kind of feed from that. But alcohols, they can be oxidized to form aldehydes, ketones, and carboxylic acids. And if you've done the previous topic, then you will have seen this before. So alcohols, basically, they can be oxidized using potassium dichromate. Now, potassium dichromate is an oxidizing agent. It's a lovely color. It's an orangey color, as you can see there. So it's the dichromate ion is orange. And it's a mild oxidizing agent, so it can actually form aldehydes, ketones, and carboxylic acids, which contain the carbonyl group, which is you'll see in a moment. And it turns actually from an orange color to a green color, which shows the chromium ion. So primary alcohols, like you would have seen this in topic. If you don't know what primary alcohol is, have a look back at topic 16, which talks about that in a little bit more detail. But basically, primary alcohols can be oxidized to aldehydes, and then it can go to carboxylic acids. So there's your aldehyde, and your carbonyl group is this. That's your carbonyl group there. Okay, it's the C double bond O. That's your carbonyl group. So aldehydes obviously contain that. And they end in al, so this one is going to be propanal because you've got 3 carbons. This one is a carboxylic acid, so it can be oxidized further to a carboxylic acid, and this forms propanoic acid, as you can see there. Secondary alcohols, they can be oxidized to ketones. Now, ketones still have this carbonyl group here, except the carbonyl group is actually in the middle of a carbon. So the difference between an aldehyde and a ketone is an aldehyde has a carbonyl group on the end carbon, it's like a terminal carbon there, whereas ketones have the carbonyl group in the middle of a carbon, so a little bit like this. So yes, and they end in -one, so this one is propanone. That's an example there. Now ketones can't be oxidized any further. Tertiary alcohols, they can't be oxidized at all using potassium dichromate. They can be oxidized through burning, so you can burn them if you want, but obviously for the purposes of this, we're just going to be looking at carbonyl groups. So how can we make these then? How can we produce these compounds containing the carbonyl group? Well, we can look at different methods in which we can make that. And depending on which method you use will depend on what products you can get from it. We're going to use an oxidizing agent, which is obviously a potassium dichromate, and we symbolize that or represent an oxidizing agent as O in a square brackets, and you'll see that later on in the in these equations here. So let's start with your primary alcohol first. So there's your primary alcohol, oxidizing agent in tow, which is in there, and that's obviously going to produce your aldehyde, which is here. So that's the first oxidation process. This is propanol. However, if we just heated this with an oxidizing agent, say in a test tube or something, you would never do that because these are obviously incredibly flammable. Then what you would get is it would basically react all the way to produce a carboxylic acid, which is obviously the next bit over here, which I'll show you in a moment. So it's really difficult to actually just get this. If you wanted your aldehyde, it's really tricky to do that. So what we have to do is remove the aldehyde. If we're looking to just take this and not get it oxidized and not proceed to further oxidation, then we need to use a method called distillation to get that. Now, distillation is basically where you have your round bottom flask and you will have your Liebig condenser effectively on a diagonal sloping downwards to a beaker a little bit further to the right. And effectively you'd heat the alcohol up, the primary alcohol, with the oxidizing agent. The aldehyde will start to evaporate, condense down the condenser, and then collect in the separate vessel. So aldehydes, you can do this because they have a lower boiling point than alcohol, so they'll kind of evaporate off much more readily. So you'd have to use a distillation setup to do that. However, if you continue to heat that and didn't use distillation, used reflux instead, then what will happen is you'll produce a carboxylic acid, which you can see here. So this is obviously produced through, obviously you'd heat that up you'd normally have like a water bath, or you might have a heating mantle. You'd put your primary alcohol in there with your oxidizing agent, heat that up, and what happens is that'll heat up, it'll hit against the condenser, cool against the condenser, and then drop back down. And then if there's an aldehyde in there, that'll oxidize further to produce a carboxylic acid, and obviously it'll basically keep going up and down, it'll keep kind of heating, condensing and dropping. And if you do that, then you'll go all the way to a carboxylic acid, which is over there. So reflux basically allows us to heat up a chemical such as an alcohol without actually losing any of the product. So if we didn't have this condenser on the top, basically we'd heat that up and all the kind of products will just vaporize and disappear. So the condenser is there to do what it says it's going to do. It's going to condense the products back into a liquid and it'll drop back down. So it's really, obviously, you probably would have seen it, I would imagine. It's a classic bit of kit to use in chemistry. Okay, so secondary alcohols, now they are oxidized to ketones. It's difficult to oxidize ketones further. Obviously, you can not using dichromates anyway. And we can obviously represent the oxidizing agent as O in the square bracket. So here's your secondary alcohol. Now, to form your ketone, there isn't any further oxidation. You only form one product when you oxidize your secondary alcohol, and that is, of course, your ketone. So in this case, we can just use a reflux setup, as I've just mentioned before, and secondary alcohols will form propanone in this case. So this is propan-2-ol, which is this one here, and that will form propanone, which is your ketone. And obviously that won't oxidize any further. So we can just put that straight into a reflux condenser like this, and that should produce the products that you need. Okay, so how do we test for aldehydes and ketones? So we know we've kind of produced them, but the problem is with aldehydes and ketones is they're colorless liquids. They don't actually have any kind of distinguishing features as such, and obviously you certainly shouldn't taste any of these at all, so definitely not. So instead we use a reagent to try and identify if we've actually got an aldehyde or if we've got a ketone. So Tollen's reagent can be used to distinguish between aldehydes and ketones. So Tollen's can be made first, and then it can be, once it's made, we can then use it to distinguish between your aldehyde and ketone. So let's see how it's made first. So first of all, silver nitrate solution. So that's what we're going to use. It's colourless. We're then going to add a few drops of sodium hydroxide until you get this pale brown precipitate that just starts to form. And then we add a few dilute drops of ammonia, or dilute ammonia, a few drops of dilute ammonia, until that precipitate starts to dissolve. And then what we have here is our reagent. This is Tollen's reagent, and this is used to distinguish between aldehydes and ketones. So then once we've got the Tollen's reagent, we're then going to add that Tollen's to either the aldehyde or ketone, whatever we have, put that in a hot water bath. Never use a Bunsen burner because obviously aldehydes and ketones are flammable. You don't want an accident at all. And then effectively your Tollen's contains a silver ammonia complex, as you can see on there. And when it's added warm, obviously it's warmed up in this beaker here, then if we have an aldehyde present, we get this lovely silver mirror that starts to coat the test tube. If it's a ketone, then we don't get any precipitate formed. Effectively, Tollen's reagent is an oxidizing agent. So all Tollen's is really doing is it's oxidizing an aldehyde, and obviously this is reduced as a result. That's what gets you silver. And obviously ketones can't be oxidized any further, so obviously it doesn't react, it just stays as it is. So if you get a silver mirror, you know you've got yourself an aldehyde. Okay, we can also use another substance called Fehling's solution. Now, Fehling's is another one which you can use to distinguish between aldehydes and ketones. A bit like Tollen's reagent, Fehling's is also an oxidizing agent, and it will oxidize aldehydes, but it won't do that with ketones. So, Fehling's solution is blue. It contains copper 2+ ions, and when we add it warm, again, very similar, we have a warm bath, like a water bath. Aldehydes will oxidize, aldehydes will interact with Fehling's, and the solution will go from a blue solution to a brick red precipitate, so it's a nice lovely colour. Ketones won't do anything, it'll just remain blue, there's no change there. So it's another test to identify aldehydes and ketones, or distinguish between them. So Fehling's is copper 2+ ions dissolved in sodium hydroxide, that's basically all it is. Okay, so how do we test for the carbonyl group in general? So obviously them two tests will distinguish between ketones and aldehydes, but ketones and aldehydes, they both have a carbonyl group, so that's fine if we want to distinguish between it. But what if we just want to know if there's a carbonyl group there in the first place? Well, we can use something called Brady's reagent. So there's a lot of people's names here, isn't it? We've got Fehling's, Tollen's, and Brady's. So Brady's reagent is 2,4-dinitrophenylhydrazine. Try and say that one quickly, which is just 2,4-DNPH, and that can be used to help identify a carbonyl group. So Brady's reagent is basically dissolved in concentrated sulfuric acid, and we mix it with a bit of methanol, and then we add that to the substance that we want to test. Now, if a carbonyl group exists, then a bright orange precipitate is formed. Now, crucially, this will only react with carbonyl groups in aldehydes and ketones. So this Brady's reagent is really good to distinguish if you have an aldehyde or ketone in the first place. And then if you do, you can then use either Tollen's or Fehling's to try and distinguish if it's an aldehyde or a ketone that you've got. It won't work with carboxylic acids, so that's good. So an orange precipitate, or the orange precipitate, is effectively a derivative of a carbonyl compound, which is purified through recrystallization. So basically what you'll get is you'll get this orange precipitate. You can purify this by recrystallizing it, so you put it through Buchner funnels and vacuum filtration, and different carbonyl compounds will actually produce different derivatives, which is quite handy. They have different melting points, and what we can do is we can actually measure the melting point of the kind of powder that's been formed, and that can help us to identify potentially what an aldehyde or a ketone is, or what type we've got. So it's quite an accurate way, or it's quite a nice way of actually identifying what you've got. And obviously we'd compare the melting point of this powder with a library of known melting points, and that can help you to identify what you've got. So it's quite a, you can kind of obviously, you'll get this bright orange precipitate forming that will tell you what you've got, but you can take that one step further by obviously crystallizing it, putting it into a melting point machine, and basically taking a measurement and trying to see what you've actually got. So there's a lot of kind of versatility with that particular reaction. Okay, so we're going to look at the iodoform reaction. Again, you would have seen this in the previous topic. I believe it will be topic 16. So I'm just going to briefly go through it here. Carbonyl groups. So obviously, because this is looking at the carbonyl groups anyway. So carbonyl groups that have a methyl group attached to it, they can react with iodine. And this is similar to the OH group iodoform reaction found, what you can find in obviously topic 17. I think it is topic 17, isn't it? So this is obviously the previous topic. I don't think it's topic 17. I think it's topic 16, should I say? Okay, so that's a slight error there. So it's topic 16. They've kind of jiggled things around a little bit. So if we heat iodine in the presence of an alkali with methyl carbonyl group, then we'll produce a yellow precipitate called triiodomethane. Okay, so basically, if we have a methyl group, a methyl carbonyl group, only exists in these two circumstances. So either in ethanol, which is this one here, so there's your ethanol, or in ketones with a methyl group. So very similar to the alcohol, in the alcohol topic, which is topic 16, not 17, so that's the previous topic, then it's a very similar process. Okay, so you might have seen that if you've looked at that previous topic. So effectively, what you would get is you've got your compound here. So this could be ethanol, for example. Ethanol reacting with iodine with a bit of your alkali that's added in there as well, and then you will produce your triiodomethane, which is this compound here, plus some iodines and water. So in this, if you see what you need to look out for, if you see any of these chemicals here mentioned in your exam, then just be aware that these can react with iodine to form this this very specific chemical, which is triiodomethane. So just be really wary of that. Any situation where it looks like that, because they might be starting to be asking questions around that. So just be really aware of that, okay? Anything other than this setup, this won't apply. Okay, so let's look at the reduction of aldehydes and ketones. So we looked at the oxidation of alcohols to form aldehydes and ketones, and now we're just going to go backwards, effectively. So aldehydes and ketones, they can be reduced to form your primary and secondary alcohols that we looked at before. Now, a reducing agent we would use is something like sodium borohydride, which is NaBH4. So we can use this dissolved in methanol and water. So we dissolve that in there. And then what we can do is reduce your aldehydes and ketones back to primary and secondary alcohols, respectively. So this should be relatively straightforward because it's basically just going backwards. Reducing agents are normally symbolized with a H in the square brackets. So oxidizing agents normally have an O in the square brackets. Reducing agents is H. So this is obviously the hydrogen in the reducing agent. That's what it's trying to symbolize. So if we start with an aldehyde first, so there's your aldehyde, and it's obviously got the carbonyl group in there. Reacting that with the reducing agent, and that will form your primary alcohol. Ketones are also reduced to your secondary alcohols. So there we are. So yours your ketone using a reducing agent to form your secondary alcohol. Now you'll notice we need 2 lots of the reducing agent, so 2 lots of H, because effectively the difference between the number of hydrogens here and the number of hydrogens there is 2. So you've got 2 additional hydrogens in this molecule compared to this one. So effectively you need 2 lots of that reducing agent to provide the hydrogen needed to reduce it in the first place. Likewise with the ketone as well. So just make sure that's the reason why it's got 2 there rather than just the 1. Okay, so let's have a look at some other reactions involving the carbonyl group. So this one is potassium cyanide. Now, potassium cyanide can react with carbonyl compounds to produce hydroxynitriles. So effectively the reaction occurs via nucleophilic addition, and you probably would have seen in topic 13, which is the introduction to, I think it's topic 13, is the introduction to AS organic chemistry. You would have seen the different types of reactions that you have. So this one is nucleophilic addition. So we have a nucleophile, which means it's a nucleus-loving species. So basically, it's a species that will go towards something which has got a delta positive or positive charge. Nucleophiles must have a lone pair of electrons as well. That's really important. And addition, because we're adding to the actual molecule. We're not swapping something or removing something. It's just addition. So we've got a nucleophile, which in this case is going to be the Cn- ion. It attacks the carbonyl group and adds on to make a hydroxynitrile and a hydroxynitrile molecule. And basically this contains an OH and a Cn group as well. So let's have a look. So we've got potassium cyanide is used to produce the Cn- ions, and when we dissolve that in acidic solution, it dissociates and you form your K plus and your Cn- ions. So effectively, that's what we start with first. That's like our pre-reaction. Okay, so let's have a look at the mechanism for this. So you can see we've got our aldehyde here, and you've got your carbonyl group with your delta positive and delta negative charges. So you've got this electronegativity difference here. There's your nucleophile, this is your cyanide ion, and that comes from potassium cyanide. That comes from there. This is a nucleophile. It has that lone pair of electrons. So this nucleophile is obviously going to go in and attack the delta positive carbon here, and the lone pair of electrons obviously start to be donated into that carbon. Now, this carbon will now have 1, 2, 3, 4, 5 bonds. So one of these bonds will break, and it's going to be this one, this pi bond. There we are. Okay, so immediately the 2 electrons from the double bond, they transfer to the oxygen, like that. So the hydrogen cyanide, obviously this is one of the, well, hydrogen cyanide could be used in this reaction, but it reacts in the same way, but with potassium cyanide, no acid is required. So it basically, hydrogen cyanide is a gas. It's really difficult to actually manage it and control it. Potassium cyanide exists as a solid. So hydrogen cyanide can also be used, and it reacts in the same way as potassium cyanide, but you don't need an acid to do that for that reaction because it exists as a gas. To be honest, most of the time you're going to be using, if you are going to do reactions like this, then it's going to be potassium cyanide you would use. It's easier to handle practically. Okay, so kind of moving on with that reaction, so you can see you're formed, or you're left with, there we are, you're left with your carbonyl group with an O minus left onto it, so basically the electrons moved onto that, and that will react with the H plus ion, and obviously this is the acid, so this is the acidified solution, so this is a supply of H plus ions in that solution as well, and this will then form your hydroxynitrile, which is formed. So you've got hydroxynitriles, I've got the Cn group and the OH group that's on there. So just make sure you're aware of all of these mechanisms because you may be asked to do these. So overall, the generic equation is this. So that's your aldehyde reacting with potassium cyanide with your acid in there from your obviously the acid that you've added in, and this will form your hydroxynitrile, and you have K plus that's knocking around as well. So there's your generic equation for the ketone as well. So it's the same types of reaction. So if we use an unsymmetrical ketone or an aldehyde apart from methanol, then we get a mixture of enantiomers that are produced. And obviously we've seen that in the optical isomerism topic. So the topic where it's about its structure and bonding. So where we look at isotopes. So you will have seen that about stereoisomers. So that's obviously going to be quite an important part. And this is where we're going to actually have a look at them. So we'll look at them in a moment. You need to know about the kind of 2 different ones that you produce. So we'll go through it after this. So when we use potassium cyanide, as I mentioned before, we need to assess the risks of using it. It can be quite risky. So just kind of make you aware of it from a practical position. Obviously, potassium cyanide, it is an irritant. You've got to be really careful when you're using it. You've got to wear gloves. Obviously you don't want to ingest it or inhale it at all, so obviously you should use a fume cupboard for it. Obviously when potassium cyanide reacts with moisture, it can form hydrogen cyanide, and that's what you don't want, so you've got to make sure you're using a fume cupboard to handle this type of stuff. And like I said, to reduce the risks, we can wear gloves when we're handling it, wear safety goggles, obviously at all times, you should do that anyway, and wear a lab coat to prevent contamination on your clothing, and obviously fume cupboard is a really, really good idea, mainly because of the potential to form hydrogen cyanide, which you don't want to breathe in at all. Okay, so let's look at some racemates. Now, this kind of feeds into the fact that you form these structural isomers that we mentioned before. So, molecules with a planar profiles, such as double bonds in the ethene topic, and you will have seen that as well, or carbonyl groups, which is this topic, then we can make what we call a racemic mix of products. So these reactions occur when we have an attack on a carbonyl group of unsymmetrical ketones and aldehydes, and that's what we were just touching on just before. So let's look at an example. Let's go into that a little bit more detail. So we've got propanal, which is C3H6O, and that reacts with acidified potassium cyanide, as we mentioned before. So the reaction between potassium cyanide and propanal involves attacking the planar C double bond O group. Okay, so obviously this is the flat bit, this is planar. And basically, as the CO part of the molecule is planar, the Cn minus can actually attack from either on the top or it can attack below. And what you form, let's have a look, there we are, or from below. And what it can form is two different enantiomers, okay, that are actually made here. So it's equally likely to form on the top or below in this example here. So the type of enantiomer formed will depend on if the CN minus attacks from the top or the bottom, and we're going to form the following. So there we are. So you've got two different mirror images of them. So either the CN is approached from one side, this side, or it's approached from that side. So you'll get this mixture of two enantiomers that have been formed. Remember, they are mirror images of each other. So due to obviously that planar nature of the C double bond O, there's an even chance for the nucleophile attacking from the top or the bottom, as I mentioned before. And this means obviously we're likely to get a 50-50 mix of both enantiomers, and what we produce is a racemic mix of products. Now, racemic mixture means you get an equal amount of each of them. So you've got two enantiomers, so we've got a mirror image of each other, and obviously they're two isomers of each other. And when we get an equal amount, we call it a racemic mixture. Okay, so there's a lot of kind of key words involved here. So, as with all racemic mixtures, and you'll see this a little bit later on in year 2, but you can detect optical isomers, which is what these are, by using plane polarized light, and it'll rotate. If you've got more of one enantiomer than another, then it'll rotate plane polarized light. If you've got a racemic mix, obviously they cancel each other out. So it gives the illusion, and again, you'll kind of look at this a lot more in year 2, so don't worry too much about it here, but it gives the illusion that when you pass a racemic mixture through plane polarized light, or plane polarized light through a racemic mixture, should I say, then it gives the illusion that you don't have any optical isomers, but you do, which has got an equal amount of each of them, and the light doesn't obviously detect that. You'll go into this a lot more into year 2, so really at this stage it's just knowing that what a racemate is and knowing what how they're formed with carbonyl groups. Okay, and that's it. So that's everything you need to know regarding carbonyl compounds for topic 17 in particular. Like I say, there is the full range of videos on Allery chemistry for the full A level for CIE. Obviously, please subscribe to the channel. Much appreciate that, just to show your support for this project as well. Like I say, these slides are available to purchase. Click on the link in the description box below from the TES shop. They're great value for money and great to complement your revision. Right, that's it. See you later. Bye-bye.